All right, so this video we're going to go over linear regression and some other things as an introduction to modeling. First thing is why do we model? Why would we do this? And the real reason to model is because with good models, we can make predictions or forecasts where we don't have data, specifically and typically into the future. That's the most common one, like you see today with climate change. However, we also can predict into different areas. We can try things with different species, so we can change elements to predict where we don't actually have any data, especially to try different scenarios. We'll talk about some of those during the course of the semester. For a little bit, we're going to focus on linear regression, probably at a level that none of you have ever focused on linear regression before. And there's a couple reasons for that. One is because linear regression is simple. It's also very powerful. We don't use it a lot in modeling because most relationships in the natural world are not linear. But linear regression is one that we can really get our heads around and how it's working. And the way it works is used in a large number of models, including all the regression or correlation models that we're going to be doing for the first about half of the semester. So first of all, need to go over the horizontal and vertical axis and the different definitions for these variables. So on the vertical axis, we have what folks have probably heard of as the dependent variable. And on the horizontal axis, we have the independent variable. So in other words, we can vary the independent one. You can't just set the vertical variable, the value for it, because it's dependent upon the independent variable or variables when we get into multiple linear regression. So the idea is that if we have some value of 30, we can go up here and say, well, we're going to get a value of around 10 for our dependent variable. So independent and dependent are two of the most common terms for those variables. However, one of the things you'll need to get used to in modeling is there's a lot of terminology and it's not always consistent. Some folks call the horizontal one the explanatory variable, because it explains what's happening with the response variable, the variable that responds to the explanatory variables. Within modeling, especially with regression, you'll hear covariate a lot because it's the variable that covaries with the dependent or a measured value. Okay, measured value is when we measure in the field, right? And then we have covariates we're trying to correlate with those measured values. You'll also hear predictor variable, especially when we start doing predictions. And you'll hear how that explains the other variable. The control variable, the outcome, these are all different definitions, and sorry about it, you'll see more of this where there's just confusion with different definitions. You might want to take this and print it out, stick it on a wall somewhere. I will try to use independent and dependent at the start of the class, and then I'll slip into using other ones where they're used in different disciplines, and you may see different terminology used just in your discipline. Now, the horizontal axis typically comes from a raster when we're doing geospatial modeling, and the reason for that is because we want to be able to predict over a large area. So those are typically rasters. The vertical axis, or the response variables, the dependent variable, those values are usually from points, and typically we get those from the field to create the linear regression initially. So some examples would be temperature, aspect, sea surface temperature if you were doing ocean work, precipitation. On the vertical axis, height, abundance, percent, diversity, and there's a lot of these. There's hundreds of different possible vertical and horizontal axes. So the overall modeling process, and this is a generalized version. We'll talk a bit more about variance on this, but basically we observe things, right? You go out and you see, hey, look, there's trees on one side of the hills and not so much on the other side, and you'll see this phenomenon. We'll talk about it. From that, you define a theory. Well, I think that the south side's getting more sun, so it has less water, and the north side has less sun, so it retains water, and that's why there's more trees on the north side of the hills, which happens in a lot of areas, especially in Colorado, where I lived for 20 years. Here, not so much because there's plenty of water everywhere, but you will see it south of Humboldt Bay. From that, we design an experiment. We then go out and collect data. We qualify that data. Then we select a model. We'll talk a lot about model selection and estimating parameters or parameter estimation. So these two are really core to the modeling process to build the best model we can. Then we evaluate the model to see how good it is and publish our results. And in reality, then we loop back because this is really a circle that repeats over and over again. Okay, so very specifically, the model is a specific algorithm that predicts our dependent variable values. Okay, we'll talk more about that. The parameters are the value in the model that we're going to estimate. And we'll talk about these for linear regression in just a sec. You will also hear these called coefficients or estimated parameters. So all three of those definitions, in fact, coefficients is used pretty heavily. I really like estimated parameters, and you'll see why in a second. And then there's performance measures that show how well the model fits the data. Careful with interpretation of this. Performance measure doesn't tell you overall how good the model is. It just tells you how well it fits the data. Another thing we'll come back to. Okay, so if we've got a linear regression, we might use the form y equals a times x plus b. If we use that equation, that means that's our model. The model is actually that equation. And we see that here where I've taken some data, built a little set of data in Excel, and now we have y equals 0.41 times x plus 0.80. That is actually our model. And this is the general model, okay, where we have a and b, and then the fitted model. The model is fitted to our data, or our final model, or a model of best fit, number of different descriptions for that we'll talk about. That is our final model. R squared then becomes the performance measure. So you've seen all this before. R squared, okay, when we look at this for linear regression, we have y equals ax plus b, or a times x plus b. That's actually our model. That equation is our model. And that's a general form of it. Here I've taken some data in Excel, created some data, and then done a linear regression. And here's my final model, or my fitted model, okay, where I actually have the parameters a and b estimated with these values. Okay, so in this model, a and b are our parameters that we're going to estimate to fit the model. And all of that terminology is really important, and you'll be speaking that way by the end of the semester. R squared is the performance measure. So again, R squared explains how well our model explained the variance in the data or fit to the data. We'll talk more about that over the course of the semester. But recognize linear regression is important because it has these three elements that all models have. It has a model, and this is a nice simple one that we can look at pretty easily. Some of the other models are hidden. You never get to actually see the model. A and B are the parameters, so it's got two. That's nice, and we can see them estimated here. And then R squared is our performance measure. And you can see that when we create synthetic data, we get pretty good R squared values. It's a lot harder with real data. Okay, now there's some important things with linear regression. Hopefully you've heard of these before. One is that the predictors are error-free, so there shouldn't be any error in your predictors. In other words, this is another example of where you could replace that with covariates or the independent variable, right? Could be any of those things. Those are supposed to be error-free. Yeah, it's not going to happen. Linearity of response to predictors. So there should be a linear response, right? If we're doing linear regression, we should expect a linear response. And that's really rare. So we can use linear regression if it's close to a linear response. There should be constant variance within and for all predictors, or homoscedasticity. And we'll talk more about that in a second. That's really important. We'll go over it in lab as well. Independence of errors, which means that if you do a test here and then you do another test, you get a measurement here, these errors, the difference from the model, should not be dependent upon one another. We'll talk a little more about that. And then a lack of multi-collinearity. What that means is we get into multiple linear regression. If we have multiple independent variables, they should not co-vary just by themselves. They should only vary with the response variable. We'll talk about that. Also, points should be equally important, and residuals are normally distributed, and we'll talk about that as well. So, bunch of assumptions in linear regression, and quite honestly, most of our natural resource data, in fact, most data in the world violates these assumptions, and we do linear regression anyway. Now, the reason we can do that is if we're close enough and we document why we feel we're able to do that. And again, we'll talk more about that over the course of the semester because these same assumptions stick for all of the methods that we'll use until we get to non. Okay, now linear regression works through something called ordinary least squares. Now, there's some math here. Please don't panic about math. I'm going to walk you through it. There isn't going to be a ton of math that you will need to be able to articulate how it works in this class because we use computers to do most of that, but there will be some, and this is certainly part of it because it's really pretty simple. I know you've heard that before from mathematics, stats people, but trust me for a little bit. Okay, so ordinary least squares. The goal here is, again, prediction and forecasting. We want to find the best fit of a line such that we minimize the sum of the square of the residuals. Okay, don't worry about that for a second. It starts with the equation of a line, okay? Y sub I equals A plus BX. Same thing we've done before, just a little bit different arrangement for A and B. Again, if we go back here, yep, I've got A and B arranged differently, but same idea. A is our intercept, B changes the slope of the relationship between X and Y. From this, we can then get a predicted value. In other words, for any value of X, we can go up to our line, which is this equation, and we can go over and get a value for Y. So for each X, there is a predicted value for Y. Okay? Now, the problem is our predicted value will not always match our sampled values. So that gives us a residual. To look at that graphically, if we go up here from 8, we hit this point. Here's our Y. Looks like it's about a 4, but it looks like in the field we measured a 5. So there's a difference of about 1 here. That's our residual. You'll also hear that mentioned as our error. Okay, and that is what's left. It's the residual, and that it's what's left over in our data that our model did not explain. Okay, so there's our predicted value of 4, and then our data was off by 5 for some reason. Could be just error in our collection process, could be a tree for some reason genetically grew faster than others. Maybe it's on one side of a rock from another where it gets a little warmer. We don't know, and our model didn't explain it. That's okay, it happens. But what we want to do is we want to minimize these residuals, right? We want to have a model that minimizes the difference between our sample values and our model. Okay, and that's really what we're doing here, is we're going to take our find our residuals, which is our sample Y sub I minus Y hat sub I. Again, that's our predicted value. And then we're going to square those. Okay, we take our residuals and we square them, because then the negatives go away and big values get bigger and small values get smaller. So it puts the emphasis on making those small values get smaller, or putting the line to where those small values go away. So we square it and then we sum them up. That is the sum of the square of the residuals. So this equation that we're going to try and minimize is the sum of the square of the residuals. And least squares applies to finding the least sum of the squares. Okay? Ordinary is just the name of the approach. All right, so to look at that graphically, which I always prefer, here again, y equals a plus bx. B is the slope, a is the y-intercept. Okay, so a would come down here. Looks like it's about a 1 in this case. And then b is going up. Not quite as fast. Oh, no, wait. Yeah, not quite as fast, about half the rate. So it looks like B is about 0.5. Our residuals will be each of these little bars. Now notice also these bars are vertical lines. The residuals are vertical. They are not the shortest distance from the line to the point, which is one of the main errors that folks get when drawing this, which I'm going to make you do. Okay, so those residuals are vertical. And then again, we're minimizing the sum of the squares of those residual distances. All right, very important stuff. Homoscedasticity. So for all that stuff that we just talked about to be valid, for the math and stats to work, these residuals need to be normally distributed along the length of our data. Okay, and that's what homoscedasticity applies to. Big fancy word that took me a while to pronounce correctly. And the basic idea is you could take a normal curve, and you'll see this in some stats books, where they put that along the line. In other words, if we took all these points and we summed up our residuals, they should make a normal curve. And if you took that at any section of our data, it should still make, the residuals should still create a normal curve when you graph them. Okay? If that's not the case, then we really shouldn't be doing linear regression, because that sum of squares is based on the belief that your residuals will be normally distributed, and that's what that means. Okay, what does normal distribution mean? You've seen this before. This is my ultimate slide for it. Graph off of Wikipedia, and there was some things added that folks struggle with. Highly recommend. It's another one to print out, put on your wall, memorize it. It's really important. Here we have the mean represented by mu. I don't know why. Greek letters, mathematicians like using Greek letters. I tend to call it the mean, but you'll also see it as mu. So that's the middle of our data, right? That's the average value. Oh, and I should also say that what we've got here is horizontally, we have the value of our residuals in the case of linear regression, right? And other regressions. So normal distribution appears in a lot of different places, but here we're using it to plot our residuals. And the idea is that along here we've got buckets, and the 34% on this side of the mean represents that 34% of our data should fall between the mean and -1 standard deviation, or -1 sigma, another Greek letter, okay? So 34%, or about a third of our data, should be between these two values. I'm sorry, a third of our residuals. A third of them should be on the other side of the mean, or positive sigma to our mean. Okay, and so this histogram, this distribution, which is also a histogram, represents the number of residuals that we would find if we put them into these buckets. Okay, and one way to check for normal distribution is to do a histogram like this and see if your residuals fall out this way. So this is where we hear that 68% of the residuals fall within 1 standard deviation of the mean, or 1 sigma of the mean. That's what that means. Could be on either side. Some people make the mistake of saying a third of the data is within 1 standard deviation. Nope, it's 2/3 because it counts for each side, or about 68%. If we go out to 2 sigma, or 2 standard deviations, then we should have 95% of our data. At 3, it's almost all of it, 99.7. And this is where you'll hear about 3 sigma being really excellent work that's being done. It's over 99% of the data, the residuals in this case, will be within 3 sigma of the mean. Now, also, you can get points way out here, and that's where some folks get confused. And sometimes you'll see min-maxes placed on data that's really normally distributed. We shouldn't do that, because you can get a big negative value, a big positive value. They're just going to be very rare. They can still happen. Okay, a little bit more detail. Just to let you know, this is how the math is done. We'll talk about this a little bit in our discussion. Okay, to be able to compute linear regression, it's not very complex math. We're just finding the mean. That's what the bar is. Mean x, mean y, our average. Mean and average mean same thing. Taking the difference from the mean. Here's the mean x, here's the mean y. Taking the difference of those, multiplying them together, summing them up, and then dividing by the square of just the x's, the difference from the mean. And that's how we compute b, the slope. And then you can find the intercept by just taking your mean y minus your b, or slope, times the xb mean. That's it. So fairly easy. A lot of the other methods will become so complicated we won't be looking at their math. Now, also, we can extend this into multiple covariates, or multiple independent variables. That's really important in what we do. In other words, we've taken y equals ax plus b, and now the b, which is our intercept, has become beta 0, just a Greek letter of the 0, and the a has become beta 1 times x, and then we can have a beta 2 times x, and I probably should have called this x1 and x2, because these could be 2 different independent variables. Could be the same, but more commonly we'll look at them with different independent variables, or covariates, or predictors. And that's where, if you had something like Douglas fir, and you're trying to predict the average size of Douglas fir after 20 years, temperature would be an important variable for that, but so would precipitation. So we want to be able to put multiple independent variables into our models, and that's through multiple regression. In this case, multiple linear regression. Now notice also the y is changed to f sub x, or a function of x. That's what that symbology means. Try not to worry too much about symbology. Just remember that f sub x, that's just a different way of saying y. All right. Okay, now, Whenever we're fitting models, we need to have some way to evaluate them. How well did the model do? Goodness of fit for linear regression is R squared, very common one. You're probably aware, well, we'll talk about it in a second. Confidence intervals are another one we use, and then there's significance with p-values. I don't recommend min-max, just don't use them. Okay, R is defined as the coefficient of determination. Here's the equation for it, and you can see again, it's kind of simple. It's just the predicted minus the mean summed together, divided by our samples minus the mean. Now, the important thing about R squared is that it will be 0 if we're basically not able to predict anything. So R squared close to 0 means we did not find a good independent variable to predict what's happening with the dependent variable. If you get an R close to 1, R squared close to 1, then yep, there you go. We are able to explain most of the variance in the data. And it's particularly easy when you do what I do and generate it in Excel. Then you can get really good data to fit your models. Now, the problem with any performance metric, which is what R squared is, it tells us how good the model performed versus our data, is it can still have issues. So, and we'll see this over and over again. I see this all the time in published papers. This looks pretty good, but you might be a little concerned if your data looks like this and here's your linear regression, right? Anybody concerned with that? I would be concerned with that. Or here's one, oh wait, that's just an outlier. We could just toss that one out. No, we can't just do that. Or here's another one. Hey, look, good R squared. All 4 of these have exactly the same R squared values. That's what's important to know. The performance metrics will not tell you if you have predictive power. They will only tell you how well your model explains what's going on in your data. Okay, and this is why you will hear me talk about how important it is to look at your data, to chart it, to plot it, and we'll do that in this class. Scattergrams, histograms, we'll put them on maps, we'll do all kinds of ways of looking at our data to figure out what's going on, and use metrics to evaluate the models as well. Like here, obviously this needs a nonlinear model, not a linear model to explain this, because as soon as we're out over here, there's no predictive power. Here we just need to find out what happened with this point. Here we have no predictive power because that's probably an anomaly. Okay? There are 2 basic approaches to building models. One is hypothesis testing. This is really the old formal one. I'm sure you've heard of it. I'm sure you may have used it in classes. It's important, it's still used. And the idea there is that we're testing whether a hypothesis is supported or not. So we create a hypothesis, and then we determine, is this supported? Now, in reality, you tend to hear about disproving the null hypothesis, which is really saying, you know, what's the chance what we're seeing is random? We want to reduce that chance that it's random. In the modeling world, especially in geospatial modeling, you will tend to hear more about which is the best model. We're always talking about which is the best model. Given a set of data, what's the best model? This assumes the hypothesis is true, and that's a little bit dangerous, right? We're assuming that our model is going to be able to do some predictions. We want to be careful of that. And the model may or may not support the hypothesis. That's really what we're saying. As we look at which is the best model, we do want to always step back and say, well, you know, this is the best one, but is it really supporting our hypothesis? And for me, it's really, is it really predicting what we believe based on natural resource research is what's happening with usually a species on the ground or in the ocean. The other approach is data mining. And this is where we just go out and find some data and try and fit a model to it. And we really discourage this. There are powerful techniques available now on computers for you to be able to do that, but we don't recommend it. It can lead to erroneous conclusions because you can find a model to fit anything. Trust me, I've done it. I can show you how. We can get perfect performance measures as long as you use a model that's complex enough, and that doesn't give us any predictive power because you try a different data set, it doesn't work. So we'll talk a lot more about that over the course of the semester. Okay, but we will focus on the middle one, which is the best model, and we just need to be careful about how we interpret that. We will use p-values, but there's a lot of confusion over p-values, most notably calling them significance. I will not call them that because I was taught that that's not what they represent. If we take into account that in h of 0 is a null hypothesis, and linear regressions would be a flat line, basically that we didn't predict anything. Our hypothesis would be that our regression line is not flat. Okay, so our hypothesis would be that using temperature and precipitation, we can predict let's say the height of adult Doug fir trees. So the p-value comes in because the p-value does is the smaller the p-value, the more evidence we have against the null hypothesis. Now, this is kind of hard to understand. In reality, the smaller the p-value, the more evidence we have that our hypothesis is true. But that's not usually the way people say it. So the smaller p-value does give us more evidence that our hypothesis is true. It's also a measure of how likely, if we went out to get another set of data, that data would not be predicted based on our model, or that the relationship that we found between our independent and dependent variables was really random. So we do want to get a small p-value. 0.1 would mean there's only a 10% chance that if we went out and collected data, our model wouldn't be able to explain it. 0.01 would be a 1% chance. So really, that's really good. Okay, we will use confidence intervals. The confusion with confidence intervals is confidence intervals are not a confidence around our data falling within the confidence interval. It's that if we went out and collected a new set of data, usually we use 95% confidence intervals, that would say that our model would appear within that 95% confidence interval. In other words, if you went out 20 times collecting data, building the same model off different data sets, 19 out of 20 times, your model's parameters would fall within that 95% confidence interval. And we use this for a lot of different things, especially in model evaluation. Model evaluation, there's a lot of different forms of that. Parameter sensitivity, that's where we're checking how sensitive our parameters are if we move them a little bit. Ground truthing is where we go back out into the field and get more data. Uncertainty in data and predictors we'll talk about a lot and the impact that has on our models. And then there's alternative models and alternative parameters. Basically with model evaluation, we always want to do is stay in the mindset of how good is this model? How do we make it better? Don't get caught up in the idea that the model is really good and is perfect and is going to predict what's going on, because it always has errors. They always have errors. All right, so when we look at this, again, where's our model evaluation? What do we draw from this model evaluation? Hopefully you'll see it's the R squared. Right? So the R squared tells us how well the model performed or how well our linear regression explained the variance in our data. Okay? So we're building models. What we're looking for is really robust models. For that, the domain or the scope is well defined. If you're predicting over 10 years of data, you don't want to say you could predict 10 years in the future or 10 years before your data. Maybe a little bit, but you got to be careful. The data is well understood. Really want to know where your data came from, how it was collected, how it was created. The uncertainty in it is documented, which is never the case. We can do that for our models, but it's really rare to get data that has uncertainty documented. We want to be able to tie it to the phenomenon. So this is really important. As natural resource folks, you want to be able to say, here's my model, and here's why it's this shape. Here's why it looks this way. In other words, this is how Doug fir trees respond to temperature and precipitation, and it shows what we would expect. That takes a deeper understanding. That your model is validated against other data. You don't want to use just one data set, try others. Sensitivity testing is where we go in and again mess with the parameters to see, is this a pretty stable model? We'll talk more about that. And that the conclusions are within the domain or scope or possibilities. In other words, I've seen folks come up with models that predicted tree height that had negative numbers in them. It's like, trees aren't negative, okay? And feel free to check out that YouTube video. All right, so I'm gonna sort of shorten the modeling process because that whole hypothesis thing we tend to skip. You're more than welcome to use it. Some professors really dictate you have to use it, but I don't. Basically, we do some investigation, we find data, we qualify the data, we go right into the modeling process, estimate the parameters, evaluate the model, and publish the results. And you will see this in the papers that we use. This is more common in modeling. Again, we need to be careful doing it, but it speeds things up and makes our results easier to communicate to a broader audience. Now, whenever we're working with data, there will be three different components. There's a trend or a correlation. That's what we've been talking about. That's what we're going to spend most of the semester talking about, is correlation methods. There is also going to be random noise that is in there, truly random effects. We'll talk about that, but you can't model them other than saying, yeah, here's how much noise is in the model. And then autocorrelation. And we're really not going to spend enough time with autocorrelation. We're going to touch on it a little bit right now, and then we're going to move right past it. but remember that it could be there, especially in certain disciplines. Okay, first law of geography. Everything is related to everything else, but near things are more related than distant things. This is what creates autocorrelation, or auto meaning self-correlating. Okay, automobile means self-mobile. So autocorrelation is self-related or self-correlated. We want to be careful of that, especially in spatial temporal data sets, because things that are closer together, like if we look at patches of aspen, you know, here you see patches of aspen close together. These trees are more similar to the trees nearby than the trees further away. Okay, so here we've got pines that are clustering and aspens that are clustering. So this is important because if you happen to do a research sample study in this area, you'd say, oh, these mountains are mostly covered by aspen. If you did it over here, you'd say these mountains are mostly covered by fir trees, and you'd miss the complexity of what's going on in the environment. So there are measures of autocorrelation, Rand's being the most common measure. From Rand's, one would be a perfect correlation. Now, we can't do that. It's really hard to model, but this is as close as we could get, like where we have our fir trees and our aspens, or pine trees and aspens, all clustered together. So things that are close together are more similar than those that are far apart. Negative correlation can happen. Perfect one would be -1. And that's where things that are close by are more different than the things that are further away. So this would be perfect negative spatial correlation. If you have a random effect, then you'll get 0 spatial correlation. So Moran's is extremely important. Some of you will need to do this in your reports or your discipline, is to check for correlation either spatially or temporally. Now, most of what we're going to do in this class, especially the first half, is going to be correlation modeling. We're going to be looking for trends that can be correlated with a known data set, model them and remove them. What we should then do is look for autocorrelation, okay? Model it and try to remove it. It can be difficult to do, so we'll just touch on that. What's left over is the residuals. There's our noise, our random effects. So this overall process is where we break down those 3 pieces, okay? Pull out the trends, try and remove autocorrelation, at least identify it if you can't remove it, and then what's left over is the residuals, also known as noise, error, random effects. And then we're going to be doing a fair bit of writing reports in this class. The reason for that is because you're going to go on to write reports and papers. This is the standard research paper format. This is what we'll be using in class. And we'll start off with doing just parts of it, and then by the end of the class, we'll be doing the whole thing. Please, again, take this one, memorize it, and have all of your stuff follow this. Don't write an abstract for the first half of the class because abstracts folks just struggle with. So we'll do that later after you're doing a good job with these papers. Thank you very much, and have fun modeling.